My name is Simon Streletsky. I work with Global Lease in Italy, and one of my challenges is delivering one of Daniel's buildings. There's some very interesting speakers to come through this session. We want to get away on time, so the first speaker up is Denoon, who's going to speak to us about wind engineering on tall buildings. Here you go.
Good afternoon, everyone. It's a real pleasure to be here this afternoon. When I look out at the audience, I see all the people who make the big decisions about tall buildings, the people who are there at the start of the design process and can guide how the developments go. And we as wind engineers don't get involved in that enough. It was a real pleasure this morning to hear Bill Baker say, it's wind engineering that really drives a lot of the design. So the talk today is pretty much on theme with the twisting, tapering, tilting. What can we do early on in the design process? What's the effect of changing the shape of a building on the wind loading? How does that affect the economy of the building? So the first thing we'll do, we'll have a little look at a movie here. This is just in the wind tunnel. And what we've got is we've got the wind coming towards us. That's effectively a tall building. It's a tall circular building sitting in the wind. And as we zoom in on the top floor, you can see it's vibrating. And what you'll see is this slowly builds up and builds up. And just ask yourself, do you fancy sitting in the top story of that building? Nice, comfortable environment? I don't think so. So what can we do about that? Well, what's the theme of the conference? Twisting, tapering, tilting. Let's try adding a twist and see what happens. Here we go, exactly the same building, and all we've done is we've added a little twist around the outside of it. Now as we zoom in, what you'll see is that it's still moving in the wind, but the amplitude is a lot less. Everything is exactly the same, but it's moving a lot less, just with that tiny little twist. So what that's telling us is that making very small changes to architecture, to the geometry of the building, can have a massive effect on the performance of the building and the cost of the building. Now what we were looking at there is what we call crosswind vibration, where it's vibrating perpendicular to wind direction. There's also another type of dynamic response there, which is a long wind response, and that's a buffeting and a drag response. So this is just looking at the long wind response, and what we can see is we can see the building getting buffeted by the wind. You'll see it's a much less regular motion than we saw with the crosswind motion. And here's where we run into one of the downsides of the upside of the twist, is that by adding that twist, we've actually made this response slightly worse. So if we were looking at that from above, and looking at the vibration, that is the sort of the path that we would see it prescribe. What we can see is the larger deflections, the larger vibrations are in the crosswind direction. So let's think about the drag first, because that's the very first thing we think about with a tall building. And these are just some very typical drag factors for different shapes. And that's straight away an indication of the load. So we look at a circle there, we've got a drag factor of 0.6. If we turn that into an oval, it can be 0.3 one direction, 1.5 the other direction. You say, well, is that a wind? That depends where in the world you are. If you're in a place where the wind comes from one direction and you can line up your building to take advantage of that, great, you're on a winner. Square, huge drag factor. Triangle, obviously, very different with direction. The triangle, as well, is a shape that we usually really don't like in wind engineering. It's a huge crosswind response. Now this crosswind response, what is it? Well, this is looking above our cylindrical building. We've got fluid going right to left. I've just done this on a water table. So what you see there is you see vortices being shed from it. And you can see that's got a very regular pattern. You can see it's got a very steady frequency. And what that's doing is the flow is separating from one side and then from the other side. And it's pushing and pulling the building backwards and forwards. That's the basic aerodynamics we need to understand. That, if we want to knock out the crosswind response in the building, is what we've got to deal with. We've got to say, how do we stop that happening? So the first thing we want to look at is, if we look at, that's just a diagram of it, there's an equation. And I promise you, this is the only equation you're going to see. It's the only equation you need, it's the only one you need to understand. And it's a Struel number, which is the description, the function of the shape. And what is the Struel number? Itself is a function of shape. D is the building width, which is a function of shape. U is the wind speed, which is a function of climate. So we can rearrange that to get the frequency with which those vortices are shed. So by altering the building shape, we can alter the frequency of the vortex shedding. You say, well, how useful is that? What we don't want to happen is the frequency of that vortex shedding to be happening at the natural frequency of the building. And for those of you who are maybe not structural engineers, what is the natural frequency of the building? It's like taking a ruler, sticking it on the edge of a table, and giving it a time. It's that rate at which the building would vibrate if you plucked it. Now what we've got here is a picture of a few people lined up on top of a tall building in Australia. What are they doing? They're pushing the building. You're standing up the top, you've got 6 or 8 people there just pushing on the building, doing press-ups on the wall. What's the point of that, you ask? Well, the point is that trace down below. That's the amplitude of the building as we push on that building. What we see from here to here is the effect of people pushing and the amplitude of this drawing and drawing and drawing. That's a tiny amount of energy. That got up to the stage where people could feel that building moving. So it was up about 2 or 3 millig's, with 8 people just pushing on the wall. So what it's telling us is, if we hit the right frequency, then it takes very little energy to get a very big response out of the building. So what we want to be able to do is keep the frequency of our vortex shedding away from the frequency of the building. There's another very important concept you can see in this figure, which is what happens when we stop pushing it there, and you see the building vibrating, and the vibrations just slowly die off. The rate at which they die off is damping. So the more damping you add into your building, and this is something that Mike will be talking about, the quicker the amplitudes die off, or the harder it is for them to build up in the first place. The interesting thing about this is you're probably all used in the States, you take a concrete building thinking about sort of inherent structural damping of about 2%. This is a fairly slender building. What we're measuring there is about 1% structural damping. So let's have a bit of a look at the effect of shape on response. This is a graph, a crosswind response coefficient. You can see that's, and it's, again, that's a function of load. And then on the bottom we have reduced velocity. And reduced velocity, that equation looks very, very similar to that equation we saw for the Struel number. And all the Struel number is doing is describing where the peaks of those curves occur. So what we see is with a square section with sharp corners, we get a very large response. If we get a circular section, then we get a much lower response, but the peak response occurs at a lower wind speed. Now this can be good or bad. But generally what we're saying there is that a square, if you're in the right wind speed range with the response, potential for a much larger response than a circular section. Now why is that? Well, the film on the left, the one we saw before, with the circular section, what I want you to look at is just just in here, you'll see that where the separation occurred, you see the die moves about a little bit, backwards and forwards on the surface. If you take a square, then you've got these very sharp corners, and that's always where the flow wants to separate. So the flow says, that's where I want to separate, that's where I'm going to do it the whole time. A circle is a bit more confused. It doesn't quite know where it wants to lead. So what we want to do is, in many cases, is to move to a more circular section. How to confuse the wind. Make sure it doesn't all leave the building in the same place. How do we do that? Well, one of the other things you'll see in this movie is that the frequency of the vortices between them is very, very different. Same flow speed, very different. So that's effective changing shape, changing size. So that's why tapering works beautifully to help reduce crosswind response. That's why twisting helps as well, because you're moving the separation points around the building. And that's exactly what we saw with that first little spiral wrapped around the building. It's shifting the place where the wind wants to separate. So you're not getting the force applied evenly over the whole length of the building. And one of the things to think about is, where is this most effective? It's the top third of the building. With a tall building, you can practically forget what you do with the bottom half. It's all in the top third. And again, you think about your ruler stuck on the side of the table. With a long lever arm, it's much easier to get a big deflection if you push it at the top than it is at the bottom. So it's that lever arm that's important. Now, let's have a look at this. What we've said is, well, if we change the shape, we can make a big change in response. What about if we just change the frequency of the building? You can see that the frequency term here, if we change the stiffness, the natural frequency of the building, what's going to happen? Well, we can move quite a long way down quite a steep curve. Is this a good thing to do? In terms of load, yes, it can be. In terms of acceleration, if you're being driven by occupant comfort, it's not a really effective way to do it. And this is why. What I'm about to show you is two videos inside a moving building. One, the one on the left, is about a typical 200-meter building. It's got a frequency of 0.23 Hz. Just once every 4 seconds a cycle. The building on the right has got 1 Hz natural frequency. So it's effectively a much shorter building. Now what you can see is you can see a big difference in the response. What you've got is these people here swaying very gently at the low frequency. At the higher frequency, you can see some much, much more dynamic effect in there. I apologise for the wig on the person on the right. He didn't want to be identified. But this is there's a really interesting effect on how different people are affected by motion. And there's a lovely bit of publication done a couple of years ago, which classified people by their postural control and the control of their head. It was critical, and he classified them into two different categories. They're either floppies or stiffies. And Melissa here on the left is most definitely a floppy. But we also heard this morning about visual cues to motion, if you get a big torsional response. My experience is that most visual cues to motion are internal, within the building. And it's not looking outside, because that's quite hard to tell if you're surveying about a bit. It's a reference to something that's close to you in the building. We've got some liquid there, you can see it sloshing about. Toilets are a classic place to spot that. You can see the little plant here, jiggling about. So what it's telling us is, even if we stiffen up the building to a lower acceleration, it might not become more comfortable. Now, how much do you think they're moving on the outside? I mean, on the inside, we're obviously moving a lot more on the right. Let's have a look at the displacement on the outside. That's both those movies running now. What you can see is at the low frequency, you've got a very large displacement. So the high frequency is a very, very tiny displacement. But if you actually get people to estimate what the displacement is, There and there, in that building, they're going to tell you it's a lot larger. And typically, what we found was that round about 10 millig's or so at 1 hertz, and this was in a real building, people were estimating they were moving anywhere from 100 to 300 millimeters. That's 4 inches a foot for those of you not quite caught up to the modern world. There is a back exit to here, isn't there? So what we're wanting to do with shape is to confuse the wind. So if we taper it, we're effectively changing the width. We're changing the shape. The vortices aren't shed at the same rate, so that's a good thing. What about bleeding flow through there? Now, we'll hopefully have Ken Yang speaking a little later. Like to put sky gardens in. They're great. They bleed flow into the wake regions, repressurize them, cut down the dynamic response a long way. There is a downside to that, of course, which means on a windy day you don't want to be in the sky garden because it's full of wind howling through to reduce the load. One that also comes up is people like to put trees in sky gardens. This is sometimes not the best of ideas. Where else do you find projectiles 200-300 meters up in the air in a windstorm? We're going to be back to putting gravel on roofs. It's a similar effect. What about corner modifications? This is just a typical corner on a building that we tested. This was well over 400 meters, this building. Had little fins extended from the corner. We modified them, canted them in at 45 degrees. We opened up the refuge floors, the building in Hong Kong, and what we saw was 20% more load reduction, just by those tiny aerodynamic changes. So there's really big benefits to that. However, if you start chopping your corners out of buildings, you lose floor space. If you're working on a limited plot, you've lost floor space, you've lost rentable area. What do? You have to go higher. If you make your building higher, what happens? The wind loads go back up again. And we're actually doing a bit of work in conjunction with the Hong Kong University of Science and Technology, looking at some of those costs. And this is some of the very preliminary work that we've done, which is taking a tall building in the wind tunnel and normalizing it by floor area, so they get taller each time. And what we see is that there's an immediate drop in construction costs because of the reduced wind load. And it takes a long way up. You can keep hacking greater amounts out the floor before you get back up to that cost. This is starting off with 60 stories, and even just taking out enough that you need to add one more story, you get a massive reduction in cost. Now, what should happen with a higher building as well, you should be able to leverage more rental income as well. So, let's just look at 2 or 3 case examples to finish off. The Northeast Asia Trade Tower, New Songdo City, perfect example of what we like. It tapers, the shape changes continually all the way up. For the height and the aspect ratio is a very small response. Capitol Tower in Kuwait, again, what we've got is almost like those scrapes that we saw in that first slide. Works very nicely. Daniel Leaveskin's Orko Tower. This is really nice, but what we see is here, because we've almost got a square on the back and this curved shape on the front, we see very different responses from different directions. And in fact, it's very, very influenced by the surrounding buildings, the acceleration between the buildings. Another Leaveskin project, the ascent at Roebling's Bridge. This is an interesting one, not particularly tall, but quite interesting, because we came up with some huge torsional loads on it. And the structural engineer said, well, why have we got these huge torsional loads? And this is just the building with its clothes off, as it were, sitting on the sting which goes through the centre of stiffness. I said, just pop a model of your building on a stick and blow on it, what happens? Phones back 20 minutes later and said, it spins around. And I said, there's your torsional load. It's not rocket science. Bill Baker was saying this morning he couldn't find a good reason to lean buildings for wind effects. There is a good reason if you can tie them together. Because what happens is you don't get the peak load on one tower at the same time you get on the other. And so you get a fair bit of load transfer between towers. You also have a whole new challenge, which is you've got a vertical component and you've got an overhang like this. Nothing approaching the side neck load on this, the gravity loads, but nonetheless an interesting challenge. This is one of our Argentinian colleagues, Alberto Feinstein, for Renoir in Buenos Aires. What we had there was a group of buildings which were very similar and quite close together. And what we see there is we see the influence between the buildings. And this is just a bit of a visualization. You can see the impact of the vortices from one starting to drive the vortices on the other. So it has a big effect, a big interaction. So you've always got to think about the design and the shaping of your building within its context. And occasionally we come up with things that break the rules. This is a structural section we were looking at, and you can see the top plate, the basic section. It's sort of like a curved triangle. We hate triangles. They're a nightmare every time someone comes up with them. We thought this was going to be a bit lively in crosswind response. We tried something that's completely counterintuitive on this, which is putting little strips along the edge, down the corners, which should, under normal circumstances, make things worse. It actually killed the crosswind response completely. So, they're the ones that catch us out, and I'm getting the signal to stop. Thanks, Aaron.
Okay, thank you very much, Roy. So I appreciate it.